All right. Uh, in this lecture, we're looking at alternative expression of internal energy. As well, we'll also be looking for enthalpy. So we derived uh, expression for internal energy before, but this is just another alternative view. Reason for this is purpose of explanation. All right. Now, we're starting from the common definition of internal energy, which is the function of temperature and volume. All right. Now let's apply differentiation to this. That is taking the differential of the dependent function, the dependent function of which is u. All right. So we are going to say the u is equals to partial derivative of u all over the partial derivative of t, keeping v constant, the t plus the partial derivative of u all over the partial derivative of v, keeping t constant, the v. All right. So from here, we know that cv cv is equals to the partial derivative of u all over the partial derivative of t, keeping v constant. So we can therefore replace this with what? Cv. So du is equals to Cv with t plus partial derivative of u all over the partial derivative of v, keeping t constant. So let's call this equation 1. All right. We also know that our entropy, noted by S, is also a function of temperature and what? And volume. All right. So now from here as well, we'll be applying this exact equation here. So that is, we are taking the differential equation of this. So we are going to have the S to be equals to the partial derivation of S all over the partial derivation of t, keeping v constant, t plus the partial derivative of s all over the partial derivative of v, keeping t constant, dv. All right. So from here, next thing we are going to do is let's call this equation number 2. So the next thing we are going to recall carefully from the first law and the second law of thermodynamics. We know that the first law of thermodynamics says that the Q equals to the U plus P dV. And the second law says that the Q is equals to what? P dS. So we are going to replace this dq here with what? T ds. So if we do that, we can therefore say T ds is equals to what? Is equals to du plus P dv. So we are going to make du the subject. U will be equals to T ds minus P dv. All right. So now let's call this equation 3. All right. So now we are going to substitute equation 2 into equation 3 because we are having the s here and here we are having the s to be equals to this. So we are going to substitute what we have here is. So now we are going to say the u will be equals to t into partial derivative of s. Partial derivative of s all over the partial derivative of t all over the partial derivative of t, keeping v constant, with t plus the partial derivative of s, all over the partial derivative of v, keeping t constant, the v. So let me close the bracket now. But don't forget we are having minus p dv here. So we are going to have minus p. All right. So now the next thing we are going to do here is nothing but we are going to say the u be equals to, if we open the bracket here, if we open this bracket, we are going to say t the s all over the t into v the t plus t the s all over the v, keeping t constant, the v minus p the v. All right. So from this from this from this we already name this equation our equation 1. So in order not to get confused, let's name this equation our equation 4. All right. So now the next thing we are going to do is we are going to compare equation 1 with equation 4. And by so doing, we know that here we are having the t here. Here we are having the v. Or here we are having the t, here we are having the v, we are also having the v. Okay, let's factor out the v. Let's rewrite this as du to be equals to t into the partial derivative of s all over the partial derivative of t, keeping v constant, the t plus t into partial derivative of s all over the partial derivative of v, keeping t constant minus t. All right. So let's name this our equation 4 as well. Equation 4. All right. Now, so now this is the t here, this is the t here, this is the v here, this is the v here. So for us to compare equation 1 and equation 4, we know that cv will be equals to what is here, the coefficient of the t, and the coefficient of the v here will be equal to the coefficient of the v here. So we are only interested in the coefficient of the v. So the coefficient of the v here is the u all over what? All over the partial derivative of v, keeping t constant, will be equals to, that is the coefficient of the v here, will be equals to t into the partial derivative of s all over the partial derivative of v, keeping t constant minus what? This is partial derivative, is not. From here we are having partial derivative of u all over partial derivative of, because this is the v, this is the v, the coefficients are equal. All right. Now let's make this our equation number 5. All right. Now you are going to recall carefully from cyclic relation, from cyclic relation, from cyclic relation. We proved this in our first video. Check out for our first video on thermodynamics derivation. All right. Now, from cyclic relation, we remember so well that to relate pressure, volume, and temperature, we are going to have the partial derivation of T all over the partial derivation of T, keeping V constant, into the partial derivation of T all over the partial derivation of V, keeping P constant, into the partial derivation of V, the partial derivation of V all over the partial derivation of P, keeping T constant. Keeping T constant is equal to what? Minus 1. All right. So from here now, the next thing we are going to do is we are going to make the partial derivation of P all over the partial derivation of T, keeping V constant, the subject. That is, we are going to divide through by what is here. So now if we do that, we are going to have the partial derivation of P all over the partial derivation of T. Partial derivation of T, keeping V constant, will be equals to minus 1 all over what? All over the partial derivation of T all over the partial derivation of V, keeping T constant, into the partial derivation of V all over the partial derivation of P, keeping T constant. All right. So now if we do this, what we are going to have is this. If we want this to go up, we are just going to take the inverse. So it means that the partial derivation of p all over the partial derivation of t is equal, keeping v constant will be equals to minus into the partial derivation of v all over the partial derivation of t, keeping p constant, into the partial derivation of p all over the partial derivation of v, keeping t constant. All right. So from here, we are going to recall from our cubic expansion that is denoted with gamma, that beta is equal to 1 over v into partial derivation of t, the partial derivation of t all over the partial derivation of v, partial derivation of v, keeping p constant, keeping p constant. And again, we are also going to recall from the compressibility factor that k, which is denoted by k, is equal to minus 1 over v into the partial derivation of v all over what? The partial derivation of p, partial derivation of p, keeping t constant, keeping t constant. All right. So now what we are going to do from this part is this. Now, if you notice, you see we have this point. We have the partial derivation of v all over the partial derivation of t. All right. Please, there's just a mistake here. From our definition of beta, which is the cubic expansion, ought to be the partial derivation of v, partial derivation of v all over the partial derivation of t, keeping t constant. All right. Now, from this part now, if I make what is here the subject of formula, means I'll cross multiply here, then I can therefore say the partial derivation of v all over the partial derivation of t, keeping p constant, will be equals to beta v. All right. So we can call this our equation. Let's call this our equation 6. Equation 6. All right. And again, from here, we have the partial derivation of v all over the partial derivation of p, keeping t constant. Let's make that the subject. We are going to have the partial derivation of v all over the partial derivation of p, keeping t constant, which is equals to minus k v. All right. We call this equation 7. Equation 7. All right. So I'm going to clean up this part. All right. So now the next thing we are going to do is we've already made equation 6 and equation 7 now. So we are going to go back to this point. Oh, I did not name this equation. Okay, let's name this equation equation star. All right. So we are going to go back to equation star where we have partial derivation of p all over the partial derivation of t, keeping v constant, to be equals to the partial derivation of, that is, minus the partial derivation of b all over the partial derivation of t, keeping p constant, into the partial derivation of p all over the partial derivation of v, keeping t constant. But you will agree with me that the partial derivation of v all over the partial derivation of t, keeping p constant, is nothing but what here? Beta v. So we can replace this with beta v. All right. It's going to be, we are going to replace it with beta p. All right. Now, but if you look carefully, we have the partial derivatives of p all over the partial derivative of v, keeping t constant. But here we are having the inverse. Here we are having partial derivative of v. We are having partial derivative of v all over the partial derivative of p, keeping t constant, will be equals to minus k v. All right, but what we have here is partial derivative of p all over what? Partial derivative of v. So for us to have partial derivative of p up and partial derivative of v down, so it will look like this. It means we are going to take this up, take this down. We are going to take the inverse of both sides. That's just what it implies. So it shows that the partial derivation of p all over the partial derivation of v, keeping t constant, will be equal to 1 all over what? 1 all over, we can say minus 1 all over k v. Hope you get that. So we can replace what is here with multiply by 1 all over minus k v. All right. So I clean this part. All right. So now the next thing is the partial derivation of p all over the partial derivation of t, keeping v constant, to be equals to minus, multiply by minus is positive, and v will cancel out v. So we'll be left with beta all over what? K. All right. This is nothing but the relationship between the coefficient of cubic expansion, and this is cubic expansion and compressibility factor. All right. So now the next thing is this. You are going to note carefully that from Maxwell equation, from Maxwell equation, from Maxwell equation, you are going to note that the partial derivation of p all over the partial derivation of t, keeping v constant, is equals to the partial derivation of s. The partial derivation of s all over the partial derivation of v, keeping keeping t constant. Keeping t constant. All right. So don't forget that this one is already equals to beta over k, and we are saying this one is equals to this. So we can say everything is equals to beta all over what? All over k. All right. Now, let's go back to our equation 5. Let's go back to our equation 5, because that is the equation that involves the internal energy. And this is our equation 5. So if we go back to our equation 5, all right, so if we go back to our equation 5, we have the partial derivation of u all over the partial derivation of v, keeping t constant, will be equals to t into the partial derivation of s all over the partial derivation of v, keeping t constant, minus p. All right. Now, but don't forget, we've already established from Maxwell equation that the partial derivation of s all over the partial derivation of v, keeping t constant, is equals to what? Partial derivation of p all over the partial derivation of p, keeping v constant, everything equals to what? Beta over k. So we can replace what is here with what? Beta over k. Therefore, the partial derivation of u all over the partial derivation of v, keeping t constant, will be equals to t into what? Into beta over k minus what? Minus p. So generally, we can finally have an alternative expression for internal energy to be equals to the partial derivation of this, keeping t constant, will be equals to beta t all over k minus what? Minus p. So if you are asked to prove this, this is how you are going to go about this. Please don't forget to follow our to follow us on our WhatsApp group for more content, for more exciting content, and don't forget to like and subscribe to our channel if you love what you are seeing on your screen. Thanks.